Hi everyone, how you doing? Good morning. What a cool time. We have the chance to really engage very differently at Cisco with the manufacturing world. And there's lots of reasons why that is. It's a market opportunity for us. But there's also a transition happening. And I wanted to talk a little bit about who Cisco is and where we came from, just for those of you who maybe don't know us and want a little background and perspective. Have you ever heard of Al Gore? We helped Al Gore create the internet. We're the company behind Al Gore. But seriously, Cisco's pedigree is in bringing things together. About 70% of the nodes on the internet today are Cisco routers. And our true pedigree is in terms of connecting things that weren't connected before. And I think that's really relevant for the manufacturing space, as I've spent the first part of my career in manufacturing and then later on at Cisco the past 8 years focusing on how to bring things together in a connected way in a manufacturing environment. There's nothing more dynamic, more interesting than a manufacturing plant, and there's actually no place in the world where there's more opportunity for innovation. And we see that, and that's reflected in our portfolio of products that spans transportation, military, industrial, mining, manufacturing, of course. And that's who we are. Our pedigree is in connecting things together. So today, the theme for today is really about connecting the unconnected, the Internet of Everything. You've probably heard this term. It was first coined by an MIT researcher who had an auto ID lab back 10, 15 years ago. And it languished for the most part, this term. And it languished for the most part because of some fundamental things that hadn't happened yet. You see the numbers up here. They're pretty amazing, right? We have about the estimate is about 13 billion devices connected up. What's happening worldwide is a fabric is emerging. This fabric is connecting every part of our lives, every manufacturing plant, and it's actually growing at an exponential rate right now. And that's incredible. So if you imagine a hockey stick, we're at the bottom of the hockey stick and we're about to take off. And I see it all around us. I'd like to share a little personal example of an experience that I had 2 years ago. I had the chance to meet with a customer up in Canada. Very good customer. In fact, they had pretty much gone end-to-end with Cisco for their technology, and we were trying to figure out what they were doing. Mining company. Mining's really just another form of manufacturing. So I had the chance to tour a nickel mine. I don't know if you've ever been to the bottom of a nickel mine, but it's a little scary. We got in a box, about 6 of us, mining gear on, I swear to God, maybe 5 feet by 5 feet. It's hanging on a cable. You go down a mile straight. And by the time you get down to the bottom, the cable's so long that it's bouncing a foot. It's the steel is stretching a foot. We got down there. These guys are relaxed. I'm a little claustrophobic in this box. It was completely dark. There's water dripping on us. And I'm thinking, boy, we're going to the bottom of the world here. I mean, what's this going to be like? In fact, these mines are so big that wasn't even the deepest mine they had. They have mines that go almost 2 miles deep, and then they have different levels that go out, sometimes 6 miles horizontally. So our tour was to figure out how they were using our technology in this enormous manufacturing environment. And it really kind of plays into this idea of connecting the unconnected. Because we got down there, we started going through the tunnels. I noticed that as we moved, the lights turned on. So the tunnel was illuminated. And we got to certain stations, and guess what? They had control systems at different points along the tunnel, just like you'd find in a manufacturing plant. And then maybe about an hour into the tour, we're probably a mile horizontally now from the original shaft that we went down in, and one of the engineers gets a call. Pulls it, I hear the phone ring, pulls out, and it's his daughter. And his daughter wants to talk to him about picnic plans for this Sunday. And I'm looking at him, I'm like, really? You're wired so well down here that you're taking phone calls from your daughter a mile under. And just to give you a sense of how deep this is, when they do their 3D modeling for the tunnels to position the equipment that they use, they actually got interference from gravity above them. They had a mile of Earth above them, and it messed up the gyroscopes. That's how deep we were. Why are they connecting like this? Why are they connecting everything? Why was everything in that mine wired? Because the degree of automation gives them such an advantage in the market that they can save energy in enormously efficient ways. They can improve productivity. They can move to extreme forms of productivity in mining operations that we've never seen before. In fact, they want to auto-ID, if you will, the whole mining complex. It took them about 12 years to just get this mine started and operational. 12-year startup time. You ever heard anything like that in manufacturing? Before you even start production? They want the ventilation systems to be on demand. So if you're a human, you're tagged, you're walking through this mine, they want the ventilation to kick in based on who you are, where you are, based on your identity. And this is a telling story because Google did it around the planet, right? I can go around the planet and find anything I want. Well, you know what? When I walk into a manufacturing plant, why shouldn't I be able to walk up to a machine? The plant knows who I am. The plant knows the machine, the fabric. I should be able to pull up information on that machine untethered. So there's so much we can do in this space. And this mining example just was perfect for describing what's possible. And that's why I wanted to open with that story and share that with you. The numbers are big, you get it, right? But let's talk about what is the Internet of Everything. It is such a marketing phrase, and yes, Cisco's guilty of coining terms and using gibberish and marketing speak and all that, but it's real, actually. And it represents a fundamental shift in our society, in our economy, and you'll find that this Moore's Law is applying in really interesting ways. Right? It's not just to integrated circuits and the density on chips, it's to production costs. For example, MEMS, which are really important for sensor technology, over a 5-year period declined 80% in cost. If you want a real comparison, almost sci-fi-like, Crae's 1A supercomputer in 1978 weighed about 12,000 pounds, cost $9 million. My smartphone right there has a couple thousand times more memory than that Crae, and probably 1,000 times more compute. That's more than NASA had when they launched the Apollo program, right in my hand. I don't think Arthur C. Clarke even dreamed that you could have that type of power in your hand and access almost every known document known to humanity through that device, all within the past 15 years. So that's what I mean by this curve. So what does that get us? Some really fundamental stuff it gets us. Allows us to monitor behavior, key in manufacturing. My manufacturing process, my control architectures, my machine health, my system health. So the first thing that we're going to look at is monitoring of behavior. Next thing is we want real-time awareness. Most of manufacturing is fixed recipe. I have a control regime. I have my manufacturing execution. And for 100 years, for the better part of 100 years, the goal was to make it a black box and run it as efficiently as possible. But the market wants something different. Our material flow is complicated. Environmentals, as I learned in casting operations, because aluminum does not like water, are complicated. And we need to move to a new regime. And guess what? I like to quote Dave McPhail. It's all about data-driven manufacturing. It's real-time awareness, right? So that's what the internet thinks. It's real. This is about feeding information into what historically have been fixed control loops, and let's move and adapt, and let's make the manufacturing environment dynamic. Let's make the machines dynamic. But there's some work we have to do to get to that vision. It's also about assisted human decision-making. This idea that there's going to be lights-out manufacturing everywhere, I don't think that's real. I don't think we're there yet. The robots are not making the robots. Well, they kind of are. If you go to Fanuc or KUKA, you probably walk into a factory and you'll see the robots making the robots, but that's another story. But human decision making, if you walk into some of the most advanced auto manufacturing plants in the world today, very often you can see one assembly line next to another. The one assembly line is mostly manual, and the one next to it is completely automated with robots. Now, the really good manufacturers don't lay off their people. They realize the value in the people, and they repurpose them. They actually have the people do even more important jobs than doing the assembly, repetitive tasks. They actually train them because now these systems need to be monitored, integrated, provisioned, troubleshooted, repaired. It's actually much more interesting. So you see the transition happening in one factory, side by side, very quickly. So what does this get us, right? Why make this investment? Why do this? Well, we want to move to flexible manufacturing. Auto is a great example. They spend hundreds of millions of dollars a year optimizing production lines as they introduce new models. That's just one example of thousands. We want to move to a vision of supply chain from start to finish in terms of material flow and execution. Obviously, energy is very often a top 1, 2, or 3 operating cost. It's hard to walk into a plant today anywhere in the world and ask a plant manager if they have visibility into line asset energy consumption. They can give you the plant numbers maybe sometimes, but do they know how that's appropriated across their production lines? No. Do they know who the top consumers of energy in their plant are? No. Mostly don't. If you go to Caterpillar, you can work it right off their public numbers. You can see, based on their green statements, that they probably spend $400 to $500 million a year on energy. And I don't know their operations well, but I would be amazed if they had asset-level visibility or process-level visibility. They're probably working towards it, right? And that's true of almost every major manufacturer in the world. But you don't have to believe me. I had the chance to present to DuPont, and I'm like a little bit of a researcher, so before I go in to meet with a customer and talk about manufacturing stuff, I like to find out a little about the customer, see what they're doing. And I happened to meet with DuPont, and they authored a paper back in 2010 with the National Science Foundation. They co-authored. Actually, there was a group of scientists and lead control engineers. And their vision, this is, 5 years ago, their vision was really compelling. It hadn't been realized yet. This was what they wanted to see in their own manufacturing footprint. And they felt compelled to do this work with the National Science Foundation to move the community to a new vision for manufacturing, one that's not fixed, one that's open and extensible, kind of like what Al Gore created, right? But with security, and we'll talk about that. But they talked about manufacturing systems that were knowledge-enabled and model-based. Create a model. When you start up, it should be as close to that model as possible. And as we get better and better and better at our real-time awareness, the model begins to converge on the actual production system. Right? This is really critical in metals and chemical process, oil and gas, but it's also kind of critical even in discrete manufacturing. Interoperable systems. Their ask of Cisco was, give me a switch that's fully managed, fully visible, has embedded compute, has all this, allows me to interconnect my distributed control systems, my intelligent machines, and I just want it to work. I want it to call home and self-provision itself in a secure way, of course. So they were thinking, and that's really where we want to head. That's really what the Internet of Things gets us. So what's the model for this? How do we think about it? There's probably a lot of work done on frameworks, data models, communications models. The first thing that I'll point out, and I'm going to come back to this at the end of the presentation, is that there's not an integrated design process for manufacturing today when it comes to how you build process, control, and communications. Process and control happen together. Communications is an afterthought. I'm going to wager right now that the companies that do all three together are going to be the winners in the next 10 years. The ones who figure out data-driven manufacturing, understand the value of connecting their assets, understand the value of data, real-time awareness, analytics-driven modeling, and behavior are going to be the winners. It's going to be the companies that don't embrace that vision that are going to be challenged. Because ultimately, you want to move to a flexible manufacturing regime, and you can't do that unless you know what's going on. It's not uncommon, for example, in consumer packaged goods environments to have, in a big plant, 3,000 or 4,000 line stoppages a day. Most of them are jams in packaging equipment. And they are absolutely struggling with how to address this problem, because if they can squeeze another 2%, if Colgate, for example, can squeeze another 2% out of its toothpaste production, that translates into 100 million extra toothpaste tubes globally. It's insane, the volumes that they produce. So data-driven, real-time awareness in manufacturing is important. And we need a model. We need a way to do this. We need a rigorous engineering approach to communications design that matches the rigorous engineering approach that historically has been there for control architecture and for process design. When I came out of school and when I went to Cisco, I was grounded in theory and fundamentals in mechanical engineering. So I relate to process very easily. It was a learning curve to understand control. That was different. But once I saw all the effort that went into ladder logic and building these control regimes, whether it was supervisory or it was embedded control in machines, I was really impressed with the amount of engineering effort that goes in. In fact, it's a principal cost in manufacturing environments to have to retool and redo your control environment as a one-off every time something changes. So that same discipline needs to be there for the communication space that is now going to be a fundamental utility, whether it's wired or wireless, not only for the movement of data for awareness, but also for control loops themselves. Because if you've been in manufacturing for a while, you'll know that there's Ethernet, control net, device net, Modbus, field bus, CAN bus, any bus, right? All these buses. EtherCAT, PowerLink, you go on and on and on, right? That happened in the enterprise 25 years ago. And the explosion in productivity that resulted after the communication wars were resolved was incredible. The planet transformed itself because we agreed on communication standards. IP/TCP guarantees that a voice call, a text message, a data packet, a video stream all gets routed across the planet. And we now have technology now where I can create control loops that extend over 100 miles if I want. Wall Street's doing it. They're bridging trading systems between Chicago and New York with millisecond delay. So I want to walk into a plant. I want to sit down with the engineering teams, and I want to think about the plant from the ground up. I know it's not going to happen day one. I know there's 10-year tooling cycles and capital investment cycles that we have to live with. We can't change that. But every time a new line goes in, we've got to think fundamentally now. In fact, if you've ever been to Hanover Fair, I went to Hanover Messe 2 weeks ago. This is aspirational, actually. Whole countries are betting their futures on advanced manufacturing, on how to think forward and be innovative in this space. So we need a model. And that model has to look at communications, data, process, control, security, this concept of identity, which is just nascent, just emerging in manufacturing. Identity's always been there. It's always lived in its silo. In this control regime, in that application space, there's always identity. It's not extensible. There needs to be a framework for security, and there needs to be a framework for communications, and it needs to be built to support control and process. It needs to be designed with control and process in mind. That's the big difference. So connecting the unconnected. How do we want to approach this? Well, I think you could break it into 3 things. You want it to be open. It seems obvious, but when I walk into a manufacturing plant and I look at their architecture, I see nothing but barriers from the top all the way down to the bottom. I see control gateways, all types of gateways, and it's hard for people to let go. It's what they know. It's what they know. Incredible amount of money is invested in architectures that are fundamentally closed and designed to protect what the manufacturer wants, or what the control vendor wants, or what the machine vendor wants, or whoever wants. Those architectures are closed. So I want to be the bitter medicine that there's a better future if together we move forward with an open vision. It's not necessarily just a pitch for Cisco. It's a pitch for how manufacturing is going to evolve whether we like it or not, because economics drives this at the end of the day. Openness wins always. Even if it takes 25 years or 30 years, openness always has to happen. KUKA, just before Hanover, announced that it was embracing time-sensitive networking, which is an Ethernet standard, for robot-to-robot connectivity. That's just enormous in the field of robotics. Because historically, all the major robot vendors really, they embraced Ethernet, but their architectures were very often closed, and they struggled with the cost of integrating their machines and robots into factories, and they've got it. Industry 4.0, Germany's national initiative around advanced manufacturing, the vision, it's just like the Internet of Things, is all about that. And they feel it coming. They know that there's a benefit to KUKA, that the companies that take the leap first and embrace the vision of openness and connectedness will be leaders in the field. And they got that. And that was really impressive. We need security. This openness can't come without security. It needs to be layered. It needs to be context-driven. That means when I connect things, there needs to be provisions for line-of-sight safety. We can't just connect things. We have to come up with mechanisms to ensure that all the safety regimes that are in place in manufacturing remain in place, and that control still rests with the operator. We can do that. There's nothing about the technology today that doesn't allow us to look at traffic, inspect it, understand the command flow, the command structure, not the protocol, not the communications, not the control protocol, not the communications. I'm talking about the payload of the packet. We can look at it and know immediately whether there's a policy violation, whether someone's trying to do a write command to a robot or a machine. Technology has existed for quite a long time. We just need the policy mechanism in place to do it. So security is huge, and we're going to talk about identity. That's going to be an evolving discussion. I think that once we elevate identity to its own plane, manufacturing systems will interconnect even much easier. And then finally, extensible. What do we mean by extensible? Historically, protocols and hardware and data types have been linked together. Like, they haven't been abstracted from each other, right? So I'll give you an example. If you've ever followed video technology, in the past, video technology had its own communications hardware, which is different from computers, which is different from phone systems. You find a lot of that in manufacturing. It's really expensive to have to put in a proprietary hardware protocol communication system for every manufacturing application you want to build. And what you get is a patchwork of systems across a plant, and then you have to hire lots of IT people, control people to figure out how to integrate it. And then when your market changes, and you need to change your retooling cycles from 6 weeks down to 1 week down to 2 days. And we see this across industries. Suddenly, that patchwork of non-interoperable systems is a business liability. So good fundamental design from the ground up will prepare you for that demand volatility and demand planning. And that's across hardware. So we need to separate hardware from protocols, protocols from data, and so on. So what is a connected factory? What we're building towards here is this idea of a connected factory. And really, for a connected factory, you're looking at machine-to-machine communications. You're looking at an open framework, an environment where it's mostly plug and play with the right policy mechanisms. You have the ability, you're not burdening skilled trades today. The average network that's put into a manufacturing facility is unmanaged, and it's put in by skilled trades. I mean, these guys are superhuman. They have to do everything. They have to keep the plant running, and then they have to be networking experts, and they don't want to be networking experts. They really don't, right? For machine vendors, this is a real challenge to get more sophisticated technology in, new services in. They're still dealing with an infrastructure in the plants that's 25 years old, unmanaged, no support. So we've got to come up with a plan to address that, to get to new business models, new manufacturing models. But what will drive this is faster time to market, faster retooling cycles, lower total cost of ownership, and really lower risk management. Machines will be connected. They will be connected to the cloud, and there will be enormous benefits to both the manufacturer and the machine vendor, and new business models will emerge. It's just the way it always goes. New business models are constantly emerging, and I think we're just at the cusp now of connected machines, machine as a service, because the value proposition to the manufacturer is huge. The ability to deeply integrate into your customers as machine vendors is impressively huge because you now become a strategic partner in their manufacturing rather than just a capital purchase with a service contract afterwards. So where are we in this evolution that's probably been occurring for a long time, right? If you've studied manufacturing, you have the first and second industrial revolutions, right? You have this emergence of automation that has gotten very sophisticated. The leading automation and control vendors today have moved to software-based platforms. There's no more just hardware-based control. In fact, PLCs themselves have converged. If you want an economic model, if you don't believe that this convergence is happening, it's been happening in the control regime forever, right? Safety used to be its own separate platform. And boy, you could get into some really big arguments with people about whether it should be converged into a single platform. That was a big deal for a long time. If you look at Siemens and Rockwell and Beckhoff and B&R, I mean, they've converged safety a long time ago. Right? They've converged other functions, I/O. They've distributed it too, and they're distributing control. So we're seeing what started out as a PC, as mainframes, moved to the PC, and then the intelligence in the PC moved back to the mainframes. But the PC still exists, right? This kind of back and forth. You're going to see that in the control world. Things converged on the control plane, and now they're being redistributed again because it makes a lot of sense economically and from a flexibility perspective. So the starting point is, where are we today? I think I have a pointer here. I don't know if it works. There we go. We're really kind of just at the tail end of phase one. There's plants that are moving towards this right here, converged plant-wide network. There's a few companies. I would say that that's the top 5% that have done that, and they're kind of maybe a third of the way through there. But most of the world in manufacturing is still here, no security. They have incredible technology in the plant, don't get me wrong. You look at the automation systems, the advanced robotics, the machining. I mean, it's mind-boggling. I'm like a kid in a candy shop every time I walk into a factory. The mechanical engineer in me comes out, and I want to just ask a million questions about how they do things. But from an architecture perspective, we're still in phase one, right? Phase two is we move to a fully connected plant, and what that really means is we have a holistic vision for the plant. We think about the plant end to end. We put in a utility, the highway system that Eisenhower invested in for this country, right? Created a utility model of infrastructure that allowed industry to blossom. Without that transportation investment, this country wouldn't be where it is economically. These utilities are important. It's time we look at communications and manufacturing in the same way. It's costly to have to reinvent the wheel over and over and over again in a plant, rather than have an extensible framework that we plug into a fabric that we connect into that has policy and governance around it, that's intelligently designed and suited for process manufacturing, discrete manufacturing, and so on. So we need to get to convergence in the plant, and then we can get to really interesting stuff, right? What's emerging now, it's all happening together, ironically. This is the funny thing. There's pressure to do all three at once. There's attempts to get machines connected to the cloud. It's going to happen. It's happening right now. We're working on projects where robot manufacturers are going to offer new service models for their robots. And they're going to connect them to the cloud, and they're going to do analytics at the edge near the robot. They're going to do it in the cloud. And they're doing this despite the fact that manufacturing IT, manufacturing control people are all saying, I don't know how we can do this. But in auto manufacturing, the vehicle systems teams, they lose $15,000 per minute when a line is down because there's too many E-stops on a robot, and the torque curve shot up, and the reducer broke. And that stops a weld line. The money's really big. So if you can predict the failure, if you can watch the torque curve, if you can know the mechanical system health, constantly monitoring, the economic reasons are there to do it. And once they realize they can do this, and IT stops being afraid of connecting to mechanical systems, there's going to be an explosion. It's not going to stop. So that's what we're seeing right now, that first curve. There have been connected robots in the past, right? But it wasn't truly connected. We weren't moving the big volumes of data we needed to, the rich data. So that's going to happen. It's happening now, but it's kind of all crunched together, and we're having to redesign, think about plants, working with old technology. And we come back to, we need a reference model. We need a place to start for how to organize this manufacturing facility. And I think an important facet here is the idea that there needs to be a data and application strategy. It's not just about laying down Ethernet and Wi-Fi in a plant. There needs to be a data strategy. There needs to be a model for how we move data. The biggest challenge we're going to have, besides communications and connectivity and overcoming all the different protocols that exist in these plants, is how do we bring different data models from all these systems together? If you talk to Memex, for example, and this is really what MTConnect is all about, is solving that integration problem that occurs as a one-off every time you want to get data off of 5 different machines with 5 different control systems. And as I learn this space, as I get deeper into it, as I'm responsible for machines and robots for Cisco, the data challenge is huge. So MTConnect provides a way to integrate these machines in a repeatable fashion in a model that's extensible. All the things that I talked about, the openness, the extensibility, are all there in that model. And that's starting to emerge all over the industrial world. The protocols are not going to go away right away, but we need an interconnect strategy, and we need a way to rapidly provision machines in a fashion that's productive and provides value. I think the statistic is there's something like 15 million, 16 million machines worldwide across 1 million manufacturing plants. 90+% of them are unconnected, which is incredible, given the state of manufacturing technology and advanced technology in the world as it exists today. So we have a model for how we integrate things, how we connect them. We want to have this idea of an extensible compute layer that can query all the diverse systems, right? You need a utility that sits there, almost like a middleware in the plant that talks to the systems in their language and then allows higher level applications and analytics and visualization tools to query that middleware. You don't want the machine being queried 50 times by 50 different applications. That's not going to scale. That's an integration nightmare. So you want to ask once, or you want to push once. You want to get it to a middle layer. And then you move the data intelligently, securely. You create an abstraction between the machines and the higher level applications, the internet and the cloud. You got to create that abstraction, right? There might be certain limited scenarios where we want to connect from the internet to a robot. Very limited, but we can have the policy and controls to protect that if we want. technology exists. But we have this edge compute, this middle layer. We accumulate the data. We normalize it. We do some cool stuff. This is exactly what MTConnect does. Connects via TCP in, takes the Shutter data format, repackages it in XML. XML is completely extensible. Everyone understands that. And then pushes it north to a consumer. And magically, someone gets OEE, yield, and availability on a machine that was never connected before. That's really valuable. But it's much richer than that. We want to know tool inventory on the machine. We want to know the status of those tools. We want to know machine health, mechanical health, system health, operating system health. We want to know all that data. It's really valuable. And then we want to know the process data. We want to know the tolerancing on the machine. So if you're the aerospace industry and you've subcontracted out a lot of your machining for critical parts and fan blades and things like that, wouldn't it be cool to know beforehand, based on the recipe that was pushed down on that machine, that the tolerances were right, that no one hacked it, and then real time build a model of the part as it's being machined so that it can be visualized and we know if the tolerances are being met. That technology exists, it's possible. I'm not saying it's easy always, but we could do that. So if we build the model right, if we build it fundamentally and we create the right abstractions so that things are open and extensible, we can begin to think that way. But with closed systems, we can't. And that's what this is all about. How do we approach this from a disciplined perspective or rigorous perspective to create a new data-driven manufacturing environment? And if you had to ask, well, what's the communications footprint look like? It's based on the Purdue model, right? This is what Cisco's Connected Plant-Wide Ethernet looks like, CPWE. We have a completely flexible model at the edge. We can move to ring architectures. We can almost emulate all the old protocols and systems that existed. You want a bus topology? We have it. You want a ring topology? We have it, right? We can do that. But what's interesting is it's very modular, number one. It's not necessarily a Cisco pitch. This is just good design. It's incredibly modular. I know this is a generic model, but the principles apply. And as dumb as it sounds, you want symmetry in your communications environment. You want it to be like artwork. Symmetry seems to matter in our lives. It's no different in communications. And the reason symmetry matters in your design, in your communications design, is because you want to know where the traffic patterns go. If you want to model the communications environment, if you want heuristics, you need a well-behaved environment. And why does this matter? It matters when things break. When things break, you need to reduce your mean time to repair to as small as possible. And today, when a sensor breaks, control system breaks, or a network breaks, you can't tell the difference. I've seen plants scramble not knowing what's going on. Because you know what? The network is not visible in the control plane. The control people don't even see the network. It should be part of the I/O tree. It should be visible to them. They should see immediately that a link went down from a control panel, from an HMI. That's happening with Siemens and Rockwell. We're doing some good work in that space, but it needs to be even more extensible than that. So there's a way to model the environment from a communications perspective, and what this really gets you is an open architecture. There's no more gateways. The PLC is still there. The I/O is still there. It can be centralized or distributed. But you have a direct access all the way down to the smallest sensor in this manufacturing footprint. You're no longer having to reprogram a PLC to get to a sensor or to get to something that's not part of the control loop, but really valuable, process data, for example. The control plane still does what it does. It's just not an application gateway anymore. It's a simple transition, but a really painful one for both manufacturer, machine builder, and control vendor. So what does this look like, right? So sensors to insights. I threw this slide in. I don't normally like to have builds, but, and I'll give you a real-life example after this, and I want to leave some time, so I'm probably going to rush through the next couple of slides so we have some time to open up for discussion, because I'd love to hear what everyone else is thinking here, right? Because I'm being a little provocative with the vision. But the idea is that, and I'll use casting as an example. A lot of casting processes are partially automated. There's a lot of manual intervention and control, even in world-class casting operations, particularly high-pressure die casting, for example. If you get 80 to 85% yield, you're world-class, and that's awesome, but you're probably doing it mostly manual, actually. It's interesting. You have control systems in there, certainly governing level systems and temperature and gradients and all types of stuff, but you're still mostly manual. It's interesting. But you have sensors that are all connected now. This is not part of the control loop necessarily, but it's really important. You capture that data. This is the big problem. How do we capture that data? What's the data model? If I have different sensors, different systems, how do I normalize that data so it's consumable and easy to visualize for an operator? Really quick, but if we follow our rigorous design principles, we have a way to normalize it, capture it, and then we analyze it, and we realize that we're beginning to creep up on a temperature threshold that's not suitable for aluminum. It's about 1,300 degrees. And we're seeing a gradient across the system. Most of these systems are gravity-fed. Interesting. They're not high pressure on the feeds. And we're seeing a gradient across the system that's unacceptable because we've got sensors connected at different points. This is something, by the way, that most manual data gathering doesn't catch real time. And what I learned about aluminum casting, because I spend my days in plants trying to figure out what's going on and really learn the tribal knowledge, because these are incredibly smart, brilliant people who do things that I can't imagine. So I sit there and try to glean off of it. You have this oxide formation. When you get too much presence of oxygen and the temperature gradients form, you get corundum. It's called corundum. The costs of that are huge. The cost of missing it is huge. You have to clean your refractories, and that's really expensive. That means you shut down your casting line. That's expensive. They don't shut down casting lines. So your analytics at the edge, real time, real fast, tell you the thresholds that are being approached from a performance perspective, independent of the control loop. And now you get to make an intelligent decision as an operator or plant manager. And you can begin to anticipate quality problems before they happen. Because when you get corundum in your castings, you get porosity. And that's a real problem in the engine industry. So really, you want those alerts to come to the operators. They want to see those performance boundaries being approached before they happen. That can only happen if you have a connected environment where the sensors are accessible, that you don't have to reprogram a gateway every time you want to get a piece of information. You want to access it directly in an open, extensible data model. And then you get to a model, communications model, where hopefully you've created a fabric and the sensor deployment is almost zero touch. It's plug and play. It's not an engineering effort to deploy additional sensors. So there's a utility model involved here in terms of your economic strategy in the plants. So let's talk about connected machines. We talked about the factory. We have a particular view on some of the problems that machine vendors face. And we think of it in terms of factory integration. I've always heard the factory side is I've got like all these machine vendors and they all want to address their machines differently and I have to consume this and it's real hard and they define how we network, you know, and everyone adjusts because it has to be done. And then from the flip side, the machine vendors want something that goes in cookie cutter. I don't want to have to do something different for everyone. I want it to go in. I want it to be consumed by the manufacturer in a very efficient way and provisioned in a very efficient way. And by the way, they have skilled tradespeople doing this, so they don't have network experts, so make it easy for me. So factory integration is really important. But then the example I just gave you of the connected sensors, this is above and beyond the control loop now, right? Connected machines, data-driven manufacturing is the next thing. I want to get smart about what's going on the machine. I want to know whether it's in cycle or out of cycle. And I want to know a lot more than that. And I want to report that up to a dashboard that I can get on an iPad or I can get in a main screen in a plant. And then we move to really dynamic connectivity, machine as a service, where we offer advanced modeling on the machines. We get data off the machines, We do analytics on it. We know and understand the wear and tear on the reducers, on the spindles, on the bearings, mechanical systems health, the the software. We're aware of this real time, and we begin to look at more of an operating model rather than a fixed capital model. And then we move into openness in time-sensitive networking. Ethernet, by the way, is not scheduled. It's kind of best effort, and this has always been the knock on Ethernet, IP networks, right? You send an email, it gets across the internet one way or another, right? Well, we can actually impose a time regime on top of Ethernet, and we can impose that with microsecond accuracy. There's nothing stopping us. The fastest networking inside machine systems today happens on an Ethernet plane with a time schedule domain on top of it, and they measure it in microseconds. So there's nothing about the technology inherently today that stops us from having very, very converged open systems that are still very fast and scheduled and guaranteed. So first order of business is connect that machine up to the plant systems. It needs a network interface that's easy to provision, that's cookie cutter, that's zero touch, that goes in, one touch. Everything behind that interface, the control regime, all the high-speed buses, everything, the variable frequency drives, the I/O, all of that remains the same, machine to machine to machine to machine. It's like the way your internet router is addressed in your home. It's always the same address on the inside. But then we want to, if we've done that right, we want to move to richer data. We don't want to just provision the machine efficiently, consume it efficiently. We actually want to get stuff off of it. Again, we come back to MTConnect and the data dictionary that exists that makes it much more cookie cutter from an integration perspective. I like this stuff. This is cool. This is really cool. On the transport layer, right, not necessarily data dictionary, which is more about kind of agreeing, all the machine vendors agreeing on the tags and what they mean, the variables, the abstraction layer. Hey, we all agree that in-cycle means this. On the transport layer, you see OPC UA emerging for transport interconnect and how we communicate broadly. It's a little different. But we've got to get that data. And very often, if you look at the 16 million machines, they don't have enough process power in them to just load software. In fact, it's invasive. They don't want software touching the control system as a retrofit. So we can offload a lot of that data acquisition, and we can query the machine. We can put an adapter in there that samples the I/O points, and we can convert that and host an MTC agent, and then move that north. That's the next phase of connected machines, right? This is a connected machine with data capture, which is just very, very, very valuable. And I think where that leads, though, in the future, it's not just acquiring the data real time. It's not just for OEE and yield, where are we? It's, I want sensor data off the machine to alert my operators of conditions that are occurring right now that are important and interesting to them, above and beyond the alarms that I get from the control system. Not all the information is captured. So there's opportunities to retrofit. And then ultimately, we want to move to machine as a service, which I think is the real economic transformation that happens, is the way machines are bought and paid for today is in a capital cycle. That's great. But let's also have an alternative for a service-oriented architecture. And the machine vendor adds additional value, special sauce, if you will, because they know how the machine operates. They've designed it. They can create the analytics. Analytics is not just a tool that you apply. Engineers have to come down, sit down, figure out the variables that matter, how they're going to be measured, and compute it. That's what analytics is really about. So it's taking your brightest and best engineers, sitting them down, capturing that tribal knowledge, moving it into automated analysis, and you collect the data off the machine. It's something the manufacturer can't do. They don't have that knowledge. And you tell them the key things they need to know about mechanical system health that keep their production up and running. That's where we're going. And that requires not just a way to acquire acquire the data off the machine, capture it via MTConnect, sorry. We have to have a framework to move the data securely. And this can be one way, if that's what the policy of the manufacturer demands, or it can be two-way. It can be bidirectional. It can give the machine vendor the ability to go in and make changes under certain conditions that are allowed for by operators, making sure that line of sight safety is there. And then finally, we move to open networking, time-sensitive networking. Ethernet becomes a converged platform for all of these communications, and we move to a more extensible model because these machines are like little factories themselves. They're not unlike a factory. They have all the elements of a complete factory all in one box, and these boxes are doing more and more and more. So I'm going to go through a couple of examples, and then I'm just going to take another minute. I'm going to come back to the casting example, because for me this was really instructive. Casting can be broke down into a melt, hold, cast, finish, lot, right, and then heat treat. It's as old as humanity. I think we've been doing that probably for about 10,000 years, except if you were to go to Honda or Chrysler or GM, they're pushing out an engine about every 60 seconds. So they do a cast every 60 seconds, and it's really one of the more impressive things you can see because you get this sense of oldness, like we've been doing this a long time, and now we've wrapped all this machinery around a process that's occurred for a couple thousand years, and we can spit out 1 million engines a year out of this process, which is, I don't know, that's pretty amazing to me. I still can't quite grasp that. And as they have robots surrounding this machine, and as you start looking into the machine, you realize how complex it is and how much data they don't have and how many points occur where quality problems can be introduced. And I'll give you a couple examples. They kind of try to measure them today. And by the way, the die-cast machines that we're seeing today, as an example, are 25 years old. I'm not going to name the company. The company that made those die-cast machines still makes the same model 25 years later. They haven't changed. I was like, can you imagine a car model being sold for 25 years? It works, though. It works. So not to make fun of it, it actually works. But I would argue we want to retrofit that existing machine, which we can do today, with an extensible data communications framework. So where are the problems that occur? Well, they have a shot sleeve that goes in. And that shot sleeve inserts the aluminum under high pressure. It's incredibly fast. And they want to measure pressure and velocity on that. In fact, they can only get a measurement once a shift. It's a real problem for them. Those two curves, pressure and velocity on the shot sleeve, tells them a ton about the quality of the aluminum, about the buildup of oxide, about the health, the hydraulic system, and how it functions as the pressure curves go up, creep up, velocity goes down. They can see the problems well in advance. And in fact, they'd like to get that data for every shot, and they do 3,000 or 4,000 a day. Then they have to take steel cylinders with a robot and insert them over bore pins. The steel cylinders are at the heart of the engine block. And this is incredibly complicated. In between each cast, they spray the inside of the die with silicone, and they want to know the temperature gradient on the die cast. So analytics on the spot, take a picture. Does the gradient match what a good temperature profile should look like for a die cast? You get where I'm going with this. And then when the robot comes over, it's got an end-of-arm effector, which is a double tool. One side inserts the cylinders, cylinder liners. The other side flips and pulls the cast out when it's done. When they insert those cylinders, the pressure at which they insert them over these specialized bore pins really matters, because if the bore pins haven't cooled sufficiently, you're going to jam that cylinder on. Here's another data point. They want to know the pressure on cylinder insert in this machine. It actually exists in the robot today, but no one can get it because the robot's not connected anywhere. They want to know that. So, and they bend bore pins sometimes. So it gets complicated here. And sometimes they bend the bore pin slightly, and those engine blocks are faulty. And they have to go to scrap in the aftermarket because now you've got steel in the aluminum and you can't simply remelt it. So knowing when you bend a bore pin and you don't go through 500 casts becomes super valuable if you can do it. So we're like a disruptor. We come in and say, so you get bent pour pins, and do you know when you bend them? Well, we find out in machining after about 3 days of inventory. That's not uncommon either. Quality control is batch after the fact. So IoT gets you real-time, data-driven quality in line with the operator knowing the problem right as it's happening. That's the value. This is a super advanced machine. I mean, I could spend a day talking about this machine. But we work the numbers backwards, and we could grow their yield over a year by 6% if we do this across all the lines. This and about half a dozen other things together that are all data-driven on an existing retrofit. So I think those numbers exist all over the place. You just have to have the courage to go in and challenge the existing models. It's a little hard because people have built their careers on them, so it's hard. You have to be sensitive. But the opportunity to learn is fantastic. The opportunity to grow is fantastic. And I'm going to jump ahead a few slides because I want to run out of time. And I had another example I was going to give you, which is really cool, which is Harley. And we can talk about that another time. But I want to come to my conclusion and maybe open up to a few questions. So what do I want you to leave with, right? How do we get to, everyone wants to get to smart, integrated, connected factories. I don't think anyone would say that they don't want to get to that. There'd be lots of arguments on how we get there. Lots of debates, good, healthy debate. Cisco certainly doesn't have all the answers, and every time I go into a plant, I meet with control, process, mechanical people, skilled trades, I learn probably more than they learn, right? That's always the equation. I'm happy about that. But they learn enough, and I challenge them on their communications models, not on their process and control. And really, we want to build a foundation. We want communications to be part of the control and process design every time, not as an afterthought. Don't design a process and a control system and then add the communications. It actually should be all together in parallel. Communications should drive the features and control and process that you want and give you the visibility and awareness that you need. So make it a foundation, and this is true, and it's been true for hundreds of years. Every time there is a foundational utility, whether it's transportation, communication, or energy, the economy grows, and it's the same thing for a plant. It's throughout history, when there's a transportation utility, communications utility, energy utility, economic value explodes. The same thing will happen in plants once we move to a communications foundation, which is ubiquitous, open, and extensible, and secure. So my ask is the next time you're involved in a retooling cycle, the next time you're involved in redesigning a machine, apply these principles. Make sure that communications and data are part of the control and design process. That means you view communications and data as an engineering process, as an engineering design process. Hopefully you'll think of Cisco, but it doesn't matter. If you design these four together and you design based on business value, on manufacturing outcomes, right, that matter, demand planning cycles, the ability to be flexible in manufacturing, this is going to empower you, and we want to be there when you do it. So I want to thank you for being here today at this keynote. This has been fantastic. I'd like to open it up to questions. We have a minute before we go. Sorry I took too much time. Any thoughts? Yes, back here. Okay, right here, sorry.
Our struggle always been is how to connect up to the IT department. I know Cisco does make several different routers, but you didn't speak about it at all. So I was kind of anxious to hear what you guys have to offer.
And the question is, let me repeat that. Your trouble is how to work with or connect to the IT department? Is that what I heard?
For example, we have several Mazaks, and we can essentially get out to the internet, but I can't get back in because of the port forwarding issue.
Yeah.
So is there any device out there that kind of can help the IT people learn how to connect up to the factory floor.
Yeah, I don't think it's a technology or device problem, actually.
No, it isn't, but
yeah.
It's still a problem.
Oh, it's a huge problem. In fact, I would say the number one barrier to connected machines, both inside and outside a plant, is IT. I have manufacturing people who are coming to us now and saying, you got to help us get through IT. And I'm like, oh, we've done this before. I think IT's scared. I think there's liability and risk, and they don't have standard operating procedures that match. So there has to be a coming together on policy, and then we can work out the technology underneath. The technology will play, and we can make the technology meet the policy needs, right? So I think it's a great question. There's no simple answer to it, I'll tell you. I've been in meetings where people are fighting.
Okay.
Yes, back here. Oh, good. Okay, thank you. Is everyone awake? Hopefully I woke you up.
Great talk, Bryce.
Thank you.
It's fantastic that Cisco is has joined the MTConnect Institute. And the question I had is, you mentioned at the beginning about hockey stick growth, and I was wondering, are there certain milestones or inflection points that you think about that are important for that hockey stick growth?
Yeah.
Thanks.
I think, for me, I think of a real world example. About 4 years ago, we went in, worked with a manufacturer, and tried to develop an energy monitoring strategy for all their major assets in their plant. We got 3 months in, and the cost of communications, the cost of the sensors was just too high, and we couldn't really develop a business case that made sense for them. It was too much. I think the key thing that we're looking for in that inflection point is the technology costs have followed that exponential drop in costs, in production costs. So MEMS, for example, are integral to many sensors. MEMS costs have fallen about 80% over the past 5 years. That's a key thing that has to happen. The same thing with RFID chips. We've seen a 40-50% drop in both passive and active RFID. So that's what we're looking for. Energy costs are falling as well. There's a number of examples where this is happening. So that's the way I look at the transition. And that's, I think, key to why the Internet of Things is exploding now, is because those production costs have begun that precipitous decline in terms of key assets that we need to make IoT real.
Bryce, it's interesting you guys are involved in the robotics side from Cisco, because I've been involved in the automation side since about the mid-90s, and we had that capability to get data out of robots since then.
Yep.
But I came out of the mold making tool and die business with the machine builders, and all my customers in 1990, when we showed a robot, said, "This is awesome, but I'll never buy one." And I said, "Why?" And they said, "Because I have no two jobs the same. Every job's got a different NC program, different configurations, and there's no way, I'm not GM, I'm not making 50,000 brake rotors a month, I'm doing something custom." And we've had that technology, but it's really kind of that cultural thing. We haven't reached the point where the customer is comfortable that a robot can do anything that it wants to, as long as the systems in control allow it to be flexible enough.
Yeah, I think that's a great point. I think the technology's been there for a long time.
Yeah, it has.
The cost of acquisition has been high, but the technology's certainly been there.
It's come way down since the mid-90s. And in the mid-90s, we only had 1 or 2 of the robot companies that even had extensible connections that you could get out of them. And today, I think across the board, all the major 6-axis ARM companies and even some of the newer technologies, it's native on the system. It may be an option you have to buy, but it's native and available there if customers want to take advantage of it.
It absolutely is. And I had the chance to present at RSA on Friday in San Francisco, and the topic was cybersecurity for connected robots. So it's made it into RSA, which is an IT bastion. And so it's coming, but you're right, the technology has been there for a long time. It really has. Any other questions? Thoughts? Good. Thank you so much for the honor to present to you today. I'm looking forward to coming back, and I'd love to, I'm open all day today to talk. So thank you again. It's been an honor.